solar heat gain calculations, section 5.3 has given this formula. It is a common formula, but still it is applicable to the marine industry also. And this formula talks about how to calculate the solar heat gains. So as you can see in this formula, which is clearly written, what is what and K is what, Ag is what, and GS, all these factors are already given. So just go through this. Being an engineer, you can easily understand what this formula all about. You can just put these values in the formula and you can arrive at the solar heat gain calculations very easily. So there is nothing much to elaborate. Being an engineer, you are already aware of this heat load calculation, so you know this formula is all about. And not only that, all guidance also is given here that in excess of temperature above say 35 degrees Celsius, then what are the values of the delta TR to be considered, that also is already been given. So again, no need to hesitate over here to use these values. Again, here also if you can see the GS, that is heat gain per square meter of glass surface, also is mentioned over here. So what GS, how much value for the clear gas, and what is the interior shading is to be considered. Normally go for the 350 being a conservative one. And also it is mentioned that surface is not included in AV because the shadow from overhanging treatments to calculate solar angle of 45 degrees. So all everything is clearly been mentioned. Just put your values and arrive at the solar gain calculations. Particular slide talks about the heat gain from the persons. As per ISO 7547 latest version, these are the values considered for the heat gain from the people. So as you can see, seat at rest and light work, there are various other values like sensible, latent heat, as typically used for the ASHRAE values. They are not different values. So for these values, these are the values you need to refer for the calculations while you are calculating the uh, heat generation or heat gain from the persons on board. So here also total value in table 4 generally same as 24 degrees Celsius, and as you could see earlier I was talking about 27 degrees Celsius. So it is mentioned there even if you design to 24 degrees Celsius, these values are not going to change. And heat values for the female should be taken 85% of the listed values, and heat emission will increase proportionately based on increasing level of activity and work level. So if you go going for sensible and light work, these are the values, and you can suppose it's a heavy work, then you can increase these values proportionately. That's what this standard is allowing you to do. So that's the basis. Of course, I told that basis is very important for oil and gas marine sector because it's linked with the insurance of the vessel or insurance of the ship or structure. So you are safe in your job. So if something happens in future, you are safe. So you can say that this is what the calculation is, it is approved and you are safe. Again and again, I'm repeating to show the importance of the basis of calculations. So again, these values we can use in the E20 form or the HAB form, whichever it is, to arrive at the calculation. Anyway, we'll be taking the case study to see how it works and case study of the entire project at the end of the module, at the end of the course. So definitely you will have some idea about it. So let's go to the next. That talks about the heat gain from lighting and other sources. It is elaborated illustrated in section 5.5. The heat gain from the general lighting as per table 4.5 is described over here. The heat gain from the lightings values are also mentioned for cabins, how much it should be for incandescent, fluorescent, LED, the mess or a dining room or gymnasium. I always suggest to go for the incandescent one because being a safer side while calculating your design heat load calculations. And then later on you can take a diversity of 20% on the entire load. That becomes a fair approach to arrive at the proper heat load calculation and the optimum one. As you know that if you over design the system efficiency comes down. So we have to design the system in a way that it serves the purpose at the rate of also it should be energy efficient also. So I suggest to go for the incandescent value, that is 15, 20, 40, and just design your system accordingly. Yeah, of course, initially it will be load would be if you find that okay, sir, the load is bit different and a bit higher. But if you see that in the cabin, the incandescent talking about 15 and fluorescent talking about 8. Gymnasiums is only one gymnasium. Mess dining room is only one. But rest all other areas you can use 15. And believe me, there's not much hard difference, very high difference you won't find in lighting load. And you can take a diversity as explained earlier, and you can close the matter. And refrigerator output, if the refrigerators are shown in the galley or the kitchen or whichever room, You can take zero point 0.3 watt per liter storage capacity unless and otherwise specified by the purchaser. For safer side, you can take, suppose you have 100 liters of fridge. So you can just this value zero point 0.3 into 100 is 30 watts. So you can add the 30 watts as a equipment load for the refrigerator. And for the temporary electrical appliances such as the television, radio set, boiler, you can be ignored as is clearly mentioned over here. The heat gain from equipment etc. in radio cabin shall be taken as 2.5 kilowatt. Its radio room is there. Equipment you can get 2.5 kilowatt as the heat dissipation from the equipment. It's clearly mentioned over here. One more important factor is heat gain from the fans shall be taken to give the rise of the temperature of the air to 1 degree Celsius per kPa of the total pressure rise. The rise in temperature of the air in the ducts should be limited to 1.5 degrees Celsius in supply duct and 2 degrees Celsius in return air duct. So this is also very important. You can check, you can see the heat gain from the fans should be taken as 1 degree at 250 kPa. So this is also very common and if you see in marine oil and gas offshore sector, crossing 1000 Pascal is very common. Sometimes we have installed fans which should 2500 Pascals. So 2500 Pascals is 2.5 kPa. So 2.5 kPa multiplied by 1 is 2.5 degrees Celsius rise uh, for the air temperature can be taken over here. And similarly, if this value is not available, you can take the limit of 1.5 degrees Celsius rise. So you suppose your ADP, apparatus dew point, and the value you will get anyways from the heat load calculations that what will be a supplier temperature over there. So supplier temperature, you need to add this value also. So you will remember at the end when it reaches to the room, how much is the increase in temperature. So you need to accordingly design your coil size to adjust this particular delta T to match your room inside conditions. Because your room supplier temperature is going to be around 14 degrees Celsius. In your room temperature, you have to maintain 24 degrees Celsius. So 14 degrees Celsius of supplier is entering inside the room. It is getting heat is getting picked up. It reaches to 24 and again enters back, goes back to the duct. So this is how the guidelines are given and which you can follow and apply for your heat load calculations to get the proper results and make it more closer to the reality.